Welcome everybody. We're in section 9.3, which we started in class the other day, and what we were learning in section 9.3 is the relationship between area and definite integrals. Alright, in this chapter so far we've been working with indefinite integrals, which means that we were integrating functions over the entirety of their domain. For most of them, that meant negative infinity to positive infinity. But now we're going to be working with definite integrals in which you're integrating over a definite domain instead of an infinite domain. Okay, now our learning goals are this. You're going to learn to find the area under a curve by evaluating definite integrals. I've shown you that in class, but we need to see a couple more examples just to solidify the idea. And then in the next video, you're going to learn some properties of definite integrals. Some very simple properties that you can use. Alright, let's get into this here. Now, I want you to read what's in the pink box. This is basically where we concluded in class, where we said when f is a non-negative function for the interval a is less than or equal to x is less than or equal to b, then the definite integral from a to b of f of x with respect to x gives the area under the curve from x equals a to x equals b. Alright, so if you look over here at this picture, if I want to find out what the area of this curve is from here to here, from a to b, all I've got to do is find the integral of the function from a to b, and there you go. That will give me the area underneath that curve. And I want to use this function over here to kind of illustrate that. You see the function that we're trying to find the area under its curve for, and we're going to have to use a definite integral in order to do that. And so according to this information that we have in this box, this property I suppose you could call it, we can say that the area underneath that curve would be equal to the integral from, now notice the x values at which this area that we're finding begins and ends. We're going from when x equals 0 to x equals 6. So indicate on our integral sign what's called the lower limit and the upper limit of integration for this problem. And then after that we're going to write the function 2/3 x, negative 2/3 x, excuse me, plus 4 dx. And for now I'm expecting you to use your calculator like I showed you in class to be able to find that integral. If you don't remember how to do it, just Google real quick finding definite integrals on TI-84, or if you're on a TI Inspire or whatever, do that search really quickly. But it's pretty simple, and what you'll find is this. The area under that curve is 12 units squared. Okay, now one of the reasons I picked such a simple function, a linear function, to integrate in this one is I wanted you to be able to see that you can use geometry to verify that this definite integral is working. Because that's just a triangle right there, isn't it? And you can see that the height of the triangle is 4, the base of the triangle is 6, so if you do half of 6 is 3, 3 times 4 is 12, you can verify that that definite integral right there actually did give you the correct area underneath the curve. And it always will, whether the curve is a straight line or whether the curve actually is what you would think of more as a curve, like what you see in that pink box right there. Alright, let's go ahead and tackle a couple more of these real quick. Alright, this time we're going to use a definite integral to find the area under the curve for the function f of x equals negative x squared plus 6x plus 7 for the integral negative 1 is less than or equal to x is less than or equal to 7. I'm going to shade that in real quick. The GeoGebra didn't really let me shade this one out of the way. It will let me shade the other pictures. Hold on a sec. Okay, so there's the shading. Now, what I'd like to see if you can do is I'd like to see if you can write the integral notation for this definite integral. I think you shouldn't have any problem with that. Write the notation and then go ahead and use your calculator to find the integral. While you pause this video, by the way, and then check here in a second to see if you got the right answer or not. I'm thinking you will. There's the integral notation that you should have used. And everything here is important. You've got to have, for a definite integral, the lower limit of your integration and the upper limit of integration. You need the entire function there if it's got more than one term in parentheses as such. You need this dx to say that you're finding the integral with respect to x and all that. Anyway, then, of course, you found out to three significant figures that this area was approximately, try to make that a couple wavy lines, 85.3 units squared. And really, it's for a problem like this where this integral idea is better than geometric formulas, because there's not a geometric formula, of course, to find the area underneath a parabola. Alright? Now, want to extend this idea a little bit further, because so far we've only been looking for the area under a non-negative curve. Or, in other words, we've been looking for area on the positive side of the x-axis, or of the y-axis, above the x-axis is what I mean to say by that. But you can use integrals as well when a portion or all of your curve is below the x-axis, as you see right here. Now I've changed the direction slightly for this because I want to focus on this area under the negative part of the x-axis, or below the x-axis. I'm saying this time to use polygons to find the area under the curve for this function that I wrote f of x right there. And I want you to then verify that that's the area by finding the definite integral on your GDC. Okay, now you see two triangles here. This triangle has a height of 7, and it is, well, it goes from negative 2.5 to negative 6, so it's 3.5 units wide. And so if you do 1/2 times base times height, you end up finding out that the area for that triangle is 12.25 units squared. Alright, then the other triangle. It looks like it is, what, 2.5 units for the base, and also, well, no, not also, but 5 units high. And so 1/2 times base times height, you're going to get 1.25 times 5. Or 6.25 units squared for that area. Okay, at this point I need to explain to you a property of definite integrals. Whenever we're talking about the area under a curve and the portion of the graph that you're finding the area for is below the x-axis, we're actually going to say that that area is negative. Alright, now I know an area of a geometric figure can't be negative, but for the purpose of calculus, yeah, we need this area to be negative anytime the portion of the curve is underneath the x-axis. So, for that one, we're going to say that the area is actually negative 6.25 units squared. And so the total area under the curve would equal that A1 plus A2, 12.25 plus negative 6.25 equals 6 units squared. And I'd like you to go ahead and verify by finding the definite integral of that function on the interval from negative 6 all the way up to 0. Go ahead and try that. Verify that we're right. And you see that you did get the same thing whenever you used your calculator to find the definite integral. Okay, so the big point to take away from here is that for any part of a curve that is underneath the x-axis, the area between the curve and the x-axis is going to be negative for that portion of the graph. Alright, I got one more for you to try now that you know that. Alright, you see the curve right here, it's got 3 regions that I'm going to label as A1, A2, and A3. And just to emphasize the part that I was saying a moment ago about when a portion of the curve is underneath the x-axis, that its area is negative for that portion, well, there's 2 different portions that would be negative. If I want to talk about the total area from negative 6 to 6, the interval that we're looking at here, I would say that the total area is going to be equal then to the opposite of A1, because if you use geometric formulas, you'd get a positive value, but we got to make sure it's negative, plus A2 minus A3. Alright, so find that area using geometric formulas, then use your calculator to verify that that's right. Go ahead. Alright, and you should have found that both the triangle for region A1 and the triangle for region A2 had areas of 4.5, and we called them negative 4.5. The triangle for region A2 had an area of 9, and then when you added those areas together, it summed up to 0, which tells us that the integral from negative 6 to positive 6 of the opposite of the absolute value of x plus 3 should be equal to 0. Hopefully you verified that on your calculator because it is true. So finding the area under a curve using a definite integral is a pretty simple thing. So far we've learned how to do that on your calculator. Of course we're going to learn how to do that without your calculator, and that's going to happen in section 9.4. Thanks for watching. I'll see you in the next video.